Hello, everybody. My name is Masood Olia, and I'm a faculty in the School of Engineering at Brentford University. And I'm here with a video related to the topic of projectile motion, kinematics of particles. And this is a very simple problem that I want to show you. I have a similar example on YouTube for, that is a problem of a ball being, a golf ball being hit by a golfer. And the reason the similarity is the fact that the surface is an incline like this one. Okay, in any case, let's take a look at this problem. Here we have water being discharged with an initial velocity of 20 meters per second, and that nozzle is 90 degrees to this surface with the slope of 3/4. And what we want to determine is at the range of the water, meaning that if it's going to land here at point A, let's say the initial point is point B right here when the water is discharged, where it's going to land. So our objective is to find R, actually. Now, I want to give you a warning. Some people get tempted to use actually to change their coordinate system. So for example, they could call this x-axis and y-axis, forgetting that actually the equations that are developed for projectile motion are based on the fact that x-axis is always horizontal and y-axis is vertical. You could actually get your equations, you have to modify your equations, because you see here how gravity, which is the total acceleration, then would have two components if you go with this x and y axis. So it's not a good idea to use this coordinate system, because then we have to modify our equations. It's better to stick with R, obviously the x-axis being horizontal and y-axis being vertical. In that case, acceleration, which is due to gravity only, has only one component in the y direction, negative y direction. In other words, we know that once this projectile is given an initial velocity, in this case, the water, the acceleration is going to have no x component. So the only gravity controls the motion, and in the y component is negative g. So the equations that I'm about to show you are developed based on the fact that no component in the x direction, 0, and because we're neglecting the air resistance, basically, that's the assumption that we do in order to come up with the equation. So this is basically a position problem, guys. So the equations that we have in the x direction, the x coordinate of the projectile going from B to A is x equal x0 initial position plus v0x, which is the initial x component of velocity, and then y equal y0 plus v0 yt, which is the initial y component of velocity, minus 1/2 gt squared. And the fact that the gravity is negative is already included in the equation. So let's pick up our coordinate system. So I'm going to call this actually positive x and call this positive y. Basically, I just changed it. I call this positive x to be to the left. All right. So this is our initial position at B. X0 is equal to 0 and y0 equals 0, because that's our reference. And what's the coordinate at A based on the x and y? So this is the x, right? And this is the y. So x would be, just looking at the slope here, 3/4, you would see x is going to be r times cosine of this angle, which actually happens to be 4/5, right? Let me actually write it down for you. So x is equal to 4/5. This is the final position of water, and the y, therefore, is going to be 3/5 of r. Okay, cosine and sine basically based on the slope. All right, so we are ready to do this, but first you have to find the initial velocity in the X and Y. We know the initial velocity is 20 meters per second. Now, notice that actually here, because velocity or the nozzle, where the velocity is leaving the nozzle, is perpendicular to 90 degrees to the surface. So we could figure out the slope or the angle. So the slope actually switches. So the run becomes 3 and the rise becomes 4. So now we have a 3 to 4. So basically you have this velocity now, right? Initial velocity with the slope of 4/3. So what is the X component of velocity? Let me go back to black. So V0X is going to be like that. And V0Y is going to be like that. So V0X, because we picked X-axis to be positive to the left, is going to be positive. So it's going to be 20 times 3/5, which happens to be 12 meters per second, right? And then V0Y is 20 times 4/5, right? And that's going to be 16 meters per second. So now we are ready to actually to plug into this equation. So X equal X0 plus V0 XT. So we start with that equation. So X is 4/5 of R, right? X0 is 0. V0X is 12 times T. So here's one equation, right? Come back to it in a minute. And then the Y is equal Y0 plus V0 YT minus 1/2 GT squared. And I'm going to plug in the information I have. So the Y is, as you could see here, is, just be careful. I forgot to put the negative. Remember that A is below the reference, right? Actually, it's negative 3/5 of R. So these are the things that you have to be careful. Negative 3/5 of R. Y0 again is 0. V0Y is 16 times T minus 1/2. And this is 9.81 T squared. All right, so two equations, two unknowns. The two unknowns are T and R. Solve it any way you like. For example, you can get R in terms of T or T in terms of R. It all depends on how you want to solve this. So for example, here, by just quick rearrangement, you see R would be 60 divided by 4T, or T is equal to 4/60R, whichever you want to use. You can solve for T and then solve for R, or solve for T directly. If you want to solve for T directly, just instead of R here, put this guy, or you can substitute for T. Regardless, either way you do it. Let me see what answers do we have. Time should be 5.1, I believe. So it's going to take 5.1 seconds for the water to get from B to A. And then in terms of R, the distance traveled along the incline, that should be 76.5 meters. Okay, guys, so this was a very simple problem I wanted to show you. As always, I really appreciate if you like the video and subscribe to my channel. I have many other playlists on topic of statics, topic of vibrations, obviously dynamics. This is related to dynamics and mechanics of materials and so on. Okay, guys, have a good day. I'll see you soon.